of heavy loads. And also, the recent pandemic has shown how our globalized society has a huge need for a better experience, not only in remote working, but in general in remote physical presence. We believe that humanoid robots can help addressing these issues. For instance, a humanoid could go in a rescue operation in place of a human operator. Humanoid robots could help to reduce the physical burden of workers, and also they could represent the means through which a human being can be present remotely and physically in a different space. But in order to do so, for sure, humanoids need to have good locomotion skills. So this leads us to the general question we are trying to address, which is how can we achieve human locomotion skills, enabling humanoid robots to help addressing current and emerging societal needs? Well, this is an old question that researchers are trying to address since some time, and in particular, after the Dark Body Challenge of 2015, a common approach to address human locomotion was to simplify the complexity of this problem by means of a hierarchical control architecture, in which every layer addresses parts of this complex problem. And in particular, the trajectory optimization layer, which basically deals with the footstep plan plus some additional optimization. Then the simplified model control layer, which sees the humanoid as a simplified model in order to compute a feasible center of mass trajectory. And finally, the whole body control layer, which sees the humanoid as a whole, considering the entire kinematics and dynamics, in order to compute the final references for the actual joints. And this loop is closed by a perception layer, which allows to measure from the environment and compute the feedbacks required by the controllers. However, this is not the only possible approach towards human locomotion, because the human locomotion task on the other side could be also learned. And in particular, for instance, learned through the reinforcement learning. So here we consider an agent which acts in an environment, and the environment that reacts to the agent by changing its own state, so evolving, and then providing the agent a reward, through which the agent can understand whether it is progressing towards the task or not. And this has been extensively used in physically simulated characters. Another possible path towards human locomotion is to look at humans and how the humans actually move. So we would collect data from human beings and exploit supervised learning in order to train some models to reproduce as close as possible the motion of human beings. And then at inference time, we can exploit these trained models in order to generate trajectories which are also human-like. Of course, in this case, it's much more difficult to, because we are not using models, so it's much more difficult to guarantee feasibility, physical properties. So this approach has been mainly developed in computer science, so where there is a virtual environment. Okay, so we can move to the more precise question we are trying to address, which is how can we exploit learning-based methods for planning and control of human locomotion? And with this research question in mind, we can briefly list the thesis contributions, which are twofold, and recall a bit the architectures that we have presented. So the first one is about deep reinforcement learning for full body human locomotion recovery, and it relates to work published in RAL in 2021. Then the second one addresses deep supervised learning for human-like human locomotion, and this refers to another RAL paper of 2022. And the third contribution is about human-like full body control of humanoid robots, which still refers to the RAL 2022 paper with some extensions. This will be the outline of the presentation, with the addition of a background and a conclusion section. So we can start with the background. How can we model a humanoid robot? A humanoid robot is basically a connection of rigid links connected by joints. And no joint is rigidly attached to the external environment, so we are dealing with a floating-based system, whose configuration is represented by the base pose and the joint vectors. And the dynamics of this system can be described by the following equation, though where the M is the mass matrix, C encodes the reducing centrifugal terms, G the gravity terms, tau the torques, and finally F are the contact ranges. But this is a complex model. And in order to deal with human locomotion, we would like to use actually simplified models. And in particular, we can do it by looking at the center of mass of this humanoid and exploit the centroidal momentum dynamics, because the rate of change of the centroidal momentum is related still to the external ranges by means of the following equation. Moreover, if we keep constant the height of the center of mass and assume zero angular momentum, then we can look at the humanoid as a linear vector. And this model, along with the introduction of the divergent component of motion, leads to a simplified dynamic of the humanoid, which considers a stable part, which is basically the center of mass following the DCM, and an unstable part, which is the DCM dynamics. So more or less, these are the models considered in the following. Then a brief introduction about DPRL. So we have seen already the basic architecture with the state, action, and reward. For us, the action will be selected through a parameterized policy by means of an artificial neural network. The transition is stochastic, so the evolution of the environment follows a probability distribution, and the reward function is defined starting from the current and next state, along with the action taken by the agent. So by interacting with the environment, the agent collects trajectories, which are sequences of triples, state, action, reward, that can be associated to a return. So cumulative reward discounted by over time. And since the goal of the agent is indeed to maximize this return, we can define a performance function, which is the expectation of the return, and then maximize it by policy items. Finally, to conclude the background, a few words about supervised learning. We start from the definition of the artificial neuron, which is basically a weighted sum plus a bias through a nonlinear activation function. Then we define the artificial neural network as a concatenation of these artificial neurons, both vertically to compose layers and horizontally to compose the network itself. And such a network, given some trained features for the multiple regression tasks of interest for this thesis, can basically be trained to minimize a loss function, so the error between the prediction of the network and the one. And this training can be performed once again through gradient descent methods. Okay, given that, we can start talking about these contributions, and in particular the first one. So deep reinforcement learning for humanoid push recovery. Now, push recovery and balancing has been addressed in the literature through control theoretic approaches, but also deep reinforcement learning based approaches. And already in 2007, Stephens was basically describing the main basic strategies for push recovery, which address different magnitude of pushes given to the human. So we start from the ankle strategy, which is just using the ankle torques, then the hip strategy, which involves the motion of the generation of momentum, and then the step strategy when the first two are not. And indeed, these strategies are basically activated one after the other based on the difficulty of the task. Now, the issue of these control theoretic approaches is that they usually address one strategy at a time with complex switching rules, and also they exploit simplified models, so the attainable behaviors in the end are somehow constant. For instance, the upper body is not so used for this studies. And on the other side, deep reinforcement learning-based approaches overcome the complexity of modeling by letting the humanoid learn this task. And here, the strategies that can be obtained are not are less constrained because the learning can produce more general strategies, but still in the literature it is always often considered a reduced action phase. So our approach, which is deep reinforcement learning, but for high dimensional balancing recovery, shares with the second category of approaches the possibility of producing many strategies with a single policy, but using high dimensional action. So basically, not only the lower body, but the entire body of the human. And we validated this approach on the simulated humans. Okay, our approach consists of an agent interacting with an environment, and then we'll see the details here. The environment provides the agent an observation and a reward, and the agent acts through an action. So we are going to characterize these three elements in order to understand our reinforcement learning. Let's start from the observation. The observation is composed of several terms. Just to have a clue of them, there are some, okay, the observation is what the agent can see about the status of the environment. There are some informations about the joint status, positions, and velocities. There are information about the base frame, so the height and the orientation, and information about the contacts. So if whether each foot is in contact, the forces at the contacts, the foot positions, and also addition with the central mass force. As regards instead the reward, sorry, our reward is composed of several components, which are summed up with the weight, with an associated weight, and then are passed through a kernel. Where a kernel is a function which basically measures an RDF kernel, measures the similarity between its input and the target. And it measures this similarity within a region of interest described or defined better through the cutoff at C. So basically, each component is associated with a weight, a target, and a cutoff. Now, since the weight and the cutoff are basically a matter of tuning, let's focus just on the target and try to understand how we would like to have each reward component at its maximum. So the reward components are also a lot based on humanoid locomotion insights, and they can be grouped in three main groups: regularizers, steady state, and transit. The regularizers are basically reward components that try to minimize the control. So in the best case, we would like to have 0 joint torques and 0 joint velocities. Then the steady state terms, which are active in double support only, they try to let the agent balance statically. So when the agent is in double support, we would like it to have its center of mass projection as close as possible to the center of the support polygon, and the postural of the humanoid as close as possible to a reference configuration, not to have the humanoid balancing weird joint configurations. Then finally, there are the transient components, which help the emergence of push recovery strategies. And just to mention some, we have, for instance, the contact forces of the feet that we would like to have equal to half the weight of the robot, so that the balance is symmetric. And then, for instance, the feet orientation that we would like to have as horizontal as possible. Finally, the agent. The agent controls the humanoid by setting velocities, joint velocities. joint velocities for 23 controller joints. So basically all the joints, but also the neck and the wrists, which are not actually very important for balancing. And in our experience, this was smoother, produces smoother qualities with respect to controlling positions there. For the training, finally, we adopted the PPO algorithm, which converges in around 20 million samples, which corresponds to 1 week of real experience. And during this training, we favored the emergence of push recovery strategies by applying some forces to the base link, forces with constant magnitude and duration. And this is the, with this setup, this is the result we managed to obtain. So you have, for instance, there an example of forward push. So the robot is pushed by a sphere frontward. And you can see how small steps and jumps emerge along with the motion of the upper body. Another example is a side push. So the robot in this case is pushed on one side, and it managed to balance on one leg before doing a final, let's say, torso adjustment. The variety of behaviors emerging from this learning pattern can be seen also in a more general setting, in which we try to exert forces which have never been seen during training. Because at training time, only forces at the base link were applied, while here we are running random, we are selecting random application points, like the arms or the torso, and so on and so forth. Also here you can see how the policy generalizes to these unseen tests. And in conclusion, for this first part of the presentation, we have seen that with this pattern, articulated full body recovery strategies emerge, which are also robust and generalized on out of samples pushes. But as you may have seen from the videos, these recovery strategies are actually most likely to be unfeasible, and also they don't look so natural. So in the end, one point to address still is the reality gap, and this is one of the possible future developments of this work. Rather than doing this, and so extending naturally the push recovery task to the working locomotion task, we decided to switch paradigm and to increase the human likeness of the overall motion by exploiting motion capture data and so data collected from humans with supervised learning. And this leads us to the second contribution of the thesis, which is indeed about the full body trajectory generation based on deep supervised learning for a human-like working, which is also a problem that has been studied a lot, as we have seen at the beginning, especially in the computer graphics community, where, however, very realistic behaviors were obtained, but still the focus was on visual appearance, and often the characters were characterized by simplified geometry, or also where their shape was changed based on human data that were collected, and so on. While dealing with robots, we don't have all this freedom. So our approach first includes a retargeting phase. So we need to take the data from the human and retarget them on the robot that has different kinematics. And in particular, we propose here a kinematically-feasible procedure for doing so. Then we interactively generate full body trajectories, and we extensively validate this system again on the iPad model. Okay, as an overview, we selected for this particular application the so-called model adaptive neural network, which is a neural network model from computer graphics adapted to different locomotion modes. This requires input features to, of course, produce prediction outputs. But in order to use this framework, we had to collect human data first, then retargeted them on the robot, as we have said already, in order to produce them those features. And at this point, we were able we were able to run the training and to allow the network to reproduce as close as possible the human. But this is not enough, because then at generation time we want to decide the motion of the robot. So we want to condition the trajectories that are generated. And for this reason, at inference time, we use this network in an auto-regressive fashion. So the previous output becomes the next input of the network. But also we allow the user via some joystick commands to condition this output before entering again into the neural network architecture. And we will briefly go through these capacities now. So let's start from the human motion capture data. To collect our data, we use the sensorized suite by Extends, which is composed by 17 IMUs positioned all over the human body, which allow to reconstruct this motion on a simplified model. And after that, we need, as we said, to retarget this motion onto the robot. In order to do so, we follow the full body geometric programming approach, which in a nutshell is an approach that finds some correspondences between the human and the robot model, and then solves an inverse kinematics in order to find the joint angles for the robot, which result into a motion that resembles as much as possible the motion of you. This approach has an issue, however, that the retargeting of the base is not taken into account. Basically, here you are seeing the motion of the human retargeted into the robot, but still with the base information from the human. So, for instance, the robot is in the air, because the human is higher, and especially as weight appears. So the robot is doing some steps that it couldn't actually perform in the real world. So what we did to solve this issue was to propose a kinematically-feasible retargeting procedure, which instead allows to obtain a kinematically-feasible motion by assuming that there is always a contact point between the robot and the ground, keeping the base orientation from the human, but recomputing the base position by lateral. So in order to maintain fixed the contact that is active with the ground. Okay, and this is an overview of the dataset that we collected and then deducted in a kinematically feasible way onto the robot. And you can see that there are different kinds of motion, forward, sideways, backward, and also mixed ones in order to let the network learn also the transitions between these different working patterns. Given the retargeted motions, we can compute some features, because the network can only see input and output features in order to learn them. And since this is not a neural network model that considers time dependency between data, we had to encode this time dependency in the features themselves. So the features will contain information also about the past and future trajectory to help the network understand at which point of the trajectory it is based on. So for the input features, we have the state of the character, so the current joint position and velocity, and some information about the motion of the base, future and past, projected on the line. So for instance, base positions, that you see in red, and base orientation, that you see in blue. Where here we are taking a frame in which the robot was basically doing a turn towards left. As regards the output, we have the state of the character at the next time step, because this is what we want to generate to generate the trajectory, but also some information again about the base projected on the ground, only in the future because the past has been already generated, still in the form of ground positions and orientations, plus some additional components. So you can have here a better view of the features computation, where the motion on the left is seen from the top on the right side, and you see that the features anticipate the motion of the robot. So for instance, now there was this turn left that we saw on the screen, and the features anticipate and follow because they cover a time window of around 2 seconds. Okay, going back to the overview, What we have, therefore, is how we computed motion capture data. We targeted them onto the robot, then we computed the features. So we were good for training. And our dataset included around 50,000 data points, around 1,000 data points, sorry, and was trained for a classic multi-regression problem, as the one that we saw at the very beginning of the presentation. And then at inference time, as anticipated, we were basically allowing the users to shape the generated trajectories by means of some input from the joystick that were processed and blended with the future part of the trajectory that is included in the output of the network. With this configuration, we managed to obtain the following results, where you are seeing here the two inputs from the joystick that are the desired motion direction, so where the user wants the robot to go, and the desired facing direction, so where the user wants the robot to face, which allows to, for instance, to differentiate between forward direction, forward walking, in which they are parallel, and side walking, in which they are orthogonal. And you can see here, okay, how these signals translate through the network into generated path. So the user is only inputting the signals, and the network takes care of generating the posture and footsteps for the full body. For instance, here you have forward walking, then side walking, and a backward walking. And it's also interesting to have a look of the different parts of the networks that activate when the motion is generated, because they basically assume a periodic phase which resembles somehow the gate of the human. Okay. So in conclusion, on this, as regards to the second part of the contribution, we show that basically efficient. We show an efficient generation because this algorithm can run basically online, because network prediction takes between 1 and 3 milliseconds for per step, and they produce diverse working patterns. So sideways walking, forward walking, also smooth transitions between them, which also, since they are learned from human data, inherit a certain degree of human likeness. On the other side, our retargeting mechanism forces us to remain, let's say, in a constrained setting, which is a flat terrain, and always keep one contact with the ground. So we are not allowed to extend directly this approach to contact-free motion or any of the rates. And this is actually one of the possible, let's say, future directions of the work. So include, for instance, perception features in order to take into account the ground. However, in the context of flat terrain, this framework showed demonstrated powerful in trajectory generation, and this is why we tried to integrate this kind of learning-based approach into existing state-of-the-art humanoid recognition controllers, which leads us to the third contribution of the thesis, which is about human-like full body control of human bodies. So the idea is to try to exploit what we saw before, so the generated pattern, to control the actual robot. So we will take both the footsteps and the posture from there. But as regards in general humanoid locomotion planners, we can say that in the literature there are many that range from those exploiting simplified models, for instance, in cycle, to plan the footsteps of the human. And these approaches are efficient, they can run online, but since they use a simplified model, the behavior is somehow constrained. For instance, the pure unicycle model cannot handle, let's say, side walk. Then, on the other side, there are models for planning that consider the full robot, and these take also into account, can take into account the dynamics, the forces, And therefore, they can produce unconstrained behavior, but on the other side, they are computationally expensive. Our approach, which is to exploit the previously presented trajectory generator for humanoid control, can stand somehow in the middle because it is efficient since it uses learning-based methods, but the behavior are not constrained. And the idea is that, again, we want to use data-driven footstep plans and data-driven time-varying posture, which comes from the training model. And we validated this approach both on ICAP 2.7 and ICAP 3, which are different evolutions of the ICAP robots. So the general architecture proposed here and named adherent basically consists of four main components: dataset collection, retargeting, trajectory generation, and trajectory control. But since we have seen already, let's say, the part about trajectory generation, which allows to generate the trajectories, we will briefly focus on the trajectory control part, which we used from an existing state-of-the-art control. So as regards the three layers of the hierarchical architecture we presented also at the very beginning, as regards the trajectory optimization layer, we do not need any external planner because we can take the footsteps, both the timings and the locations, from the neural network. As regards instead the DCM optimization, we followed the approach of previous existing work, in which basically the DCM is planned first in singular support by assuming the 7p constant in the center of the support foot, and then in double support by simulating this trajectory with the three-order polynomial. Then at the simplified model control layer, we used an existing extremely simple implementation, an instantaneous controller for the CM, which, however, does not guarantee the ceramic stability criteria. So it doesn't take into account limits, feasibility regions for the CM. For the full body control, QP control layer, again, we try to keep it as simple as possible and followed an approach which considers kinematic sound. So basically, we try to find the robot velocity that minimizes task for the torso orientation and a regularization of the joints that again comes from the learned model, and also is standard, while usually it is basically somewhat fixed posture used to regularize the working motion. This problem is subject to a constraint for the feet and center of mass. And also here, let's keep in mind that okay, no contact forces are considered, and so there is nothing about the feasibility. Following this simple three-layer architecture, we managed to exploit for actual locomotion of the humanoid the patterns generated by the network. So you can see here the kinematic visualization, where we basically reset the robot state, so we are free to change the motion as we want, against compared to the dynamic simulation. And you can see some hacks that we had to perform in order to have this working. For instance, especially now inside working, you can see that we had to scale the footsteps because the originally produced footsteps are too hard for the human to follow them without falling with this simple control infrastructure. Also, we had, for instance, to enlarge a bit the arms because the planner does not consider self-collision avoidance. But anyways, we were able to track in simulation the generated behaviors. And so we decided to move to the real robot. And you can see here the outcome of some experiments where again the footsteps were scaled, this is in real time, and also the velocity has to be scaled. Our let's say insight about this is that probably this is due to simple locomotion controller that used, or also the fact that the robot is controlling position. Anyways, you can see the emergence of, for instance, one of the outcomes is the emergence of a motion for the upper arm. So basically, the arms that follow what we usually do as humans while we move. That is pretty different from the usual, let's say, working locomotion pattern in which the posture or the upper body is fixed, and it looks more natural. Here instead you have other experiments in which the side and the backward working were performed. So we basically managed to transport on the real robot the generated patterns. After this, we decided to port this framework to a different humanoid, ICAP3, which is taller and heavier with respect to ICAP 2.5. And basically, no conceptual changes were needed because all the parts of the infrastructure are modular with respect to the robot. However, the training itself needed to be repeated again on the data retargeted for this robot. So we cannot say that the framework is optimized. It is easy to port, but of course we could investigate better, let's say, alternatives to make the porting faster. In the end, we obtained comparable working performances with the different robots. So in conclusion, for this third part, we can say that, okay, exploiting the learning-based pattern, the learning-based working generator improved the human likeness of the motion, and this framework is also adaptable to different humans. On the other side, some limitations appear when executing those trajectories on real robots, and also we are not completely exploiting the output of the network, because we said that we were using the footsteps and the posture, but we could, for instance, add some terms related to the momentum and other quantities generated by the network. So the main principal direction for future work is to try to integrate this planner with more advanced controllers. So for instance, NPC-based, like the one in the work by Humanoid 2020. And this is actually a current direction of research that is not included in Thesis because it's something we are working on later, basically. And you can see here we have yet another robot, Erika, which is another evolution of the robot. It's similar but taller and with a different configuration. And you can see, for instance, in the bottom right plot that also the angular momentum coming from the network is periodic. It follows the generated trajectories and could be exploited to warm start, for instance, in NPC against, let's say, a zero angular momentum that is usually used. So in the end, we saw the, let's say, given the research question about learning-based methods for planning and control of humanoid robots, we saw a first contribution about deep reinforcement learning for humanoid push theory, which was successful, robust, generalizes, but it didn't give us the guarantees to try to follow, to develop this approach on the other. Then we switched on the deep supervised learning approach in order to generate human-like locomotion patterns. And we executed those patterns on the real robot. So in conclusion, if we go back to the very first research question about the improvement that we can contribute to achieve for human locomotion, our thesis here is that we could, as we have done, integrate learning-based approach and model-free learning-based approaches with model-based existing control architectures. And of course, the work that we have done here is just a first step in this direction that we hope it will, let's say, improve the human likeness of the humanoid motion, and so therefore also the interaction that the humanoids in the future could have with human beings, and their acceptability and interpretability of their motions. So with this, I would like to conclude and thank all the guys I'm working with every day, and I'm open to questions. Thanks.
One general question, which is broader than what about the stability of the personal learning point?
So
something common.
in general, of course, these kind of approaches that are model free, they do not take into account models, they do not study the stability, nor guarantee the stability. So, of course, there are no formal guarantees about that. And this is one of the main issues of developing reinforcement learning-based policies on real-world learning. Because, of course, when we do experiments with real policies on real humanoids, we are always somehow scared about particular decisions that the network could take at a certain point while working perfectly nice for a long time, then something bad could happen. And of course, yeah, in the end, there are no guarantees. This is the good part.
Another question, which is also about curiosity, why you are searching for a natural data?
Okay, this is a very good question. And actually, while doing this, and searching the literature, we also ourselves realize that this often is not even taken into account. So we agree that it's possible, of course, to plan locomotion, to try to let the human work completely independent from you. Our approach instead favors human likeness, because this in general could be helpful when humanoids are going to collaborate. So let's imagine, for instance, a humanoid and a human that are carrying a table together in a working environment. If the motion of the humanoids resembles the motion of the human collaborating with him is, let's say, performs a simpler, more intuitive task from one side. From the other side, in general, human likeness of motion for those kind of particular robots which already resembles the structure of the human makes sense in order to let them more acceptable for also for the general public.
It's a social kind of
social, the human likeness itself, yeah, but also okay, maybe I didn't clarify this enough, but human likeness, if we try to mimic behavior that we know the humans as actually optimized for years, we are also going towards some efficient and feasible solutions. So this is another completely different aspect.
Only just a few curiosity. So the first is a very technical one. So you said in the last part that you tested on a robot, which is different from the 3D version. So is the difference something? Is this difference something that can impact on your methods or no?
Okay, okay, this is the slide. Well, the robots are not completely different. They are compared over there. There are differences in the height, in center of mass, in the weight. So, for instance, the legs of these three are heavier than the legs of the 2.5. So basically, there are also, of course, as regards to real robot, there are different motors, different actuators, different sensors. So it is a different platform. What we found out with those platform available, of course, with other platforms we could do more general tests, is that in transferring between these two robots, there was no conceptual change in the architecture. So apart from the details related to the, let's say, the architecture was transparent with related to the robot. Why? Because, okay, as regards human data, they were collected. As regards to targeting, the method is general. as long as those correspondences that you saw in the picture between and this file. Let me try to find them because it's as regards retargeting, basically. Yes, as long as you can define correspondences between the human and the robot model, which makes sense because if this part is missing, then it's hard to attack. But as long as you can do that, then the method is general. Feature computation is the same. Of course, the part that is maybe more related also to the robot, its dynamics and so on, is the control architecture. And in our case, the control architecture was mainly a way to show that we could bring those learning generated patterns onto the platform. So we didn't focus too much about the differences at that point. So we used the same architecture. In the end, the framework was started with no modifications.
Okay, but it's just my question or the last version is stable?
Yes. Stable, you mean like it's yeah, it's
so it is held by, of course, by the
yeah, it does,
the neutral table.
Maybe by chance. Okay, you're right. I didn't focus about that because also these are so both the robots have their own battery on board. In this particular experiment, actually, yes, there is the table, but I wasn't getting the question because I remember wrongly that also in this case, that's why the robot was because both they can be powered on board. It's just in these particular experiments we were using the cable for power. For instance, the other example there is with this robot, so we have a 2.7 but without the cable.
And this brings me to the other question. So everything was computed in the system of the robot.
The control part, yes. The trajectories can be generated online, and this is part of the work that we are doing, the last part that I was showing. For this specific experiment, they were pre-computed, the trajectories, but just because in order to generate interactively locomotion trajectories, you basically have to plan a few steps, and then after a while plan other steps, and we miss the implementation of this, let's say, iterative sequence plan. But in principle, it can be for sure done because the network prediction is very short in time, so it is not the computation expensive part of the pipeline. So the fact that all the other parts were running online basically means that the whole framework can. And this is what we are trying to do right now.
Okay. And when you said that you trained on 500,000 data points, is it was the size of the trajectory? For what?
Okay. Yes. So the trajectory is in the form of frames. So okay, screenshots of the humanoid movie at a frequency of 50 Hz. So we have 50 instances per second. Okay. And we collected around 1 hour of data. So in the end, this means that the single data points were 500,000 more or less, which includes all the kinds of motion that we have seen, plus a mirroring that we implemented in order to, let's say, rule out asymmetries that the network could have learned, because maybe in the data collection we perform a certain motion a little bit towards one side or a little bit towards the other. So there was a data plus mirroring, so double the data.
Just a second, that's the environment that is motion and involve stuff like, for example, the condition the racing feature that is involved.
It is absolutely involved, because this the experiments, the architecture that we are using here is, let's say, a lot biased by, for instance, the flatness of the ground. So if we would like to perform some experiments outside, we should either change the control pipeline, possibly, so also consider maybe try to control the rotation torque so that the contact forces are handled better. While with this position control, if the foot, let's say, for instance, impacts the ground in a slightly different configuration with respect to the assumed one, which is flat terrain, there are a lot of issues. So yeah, for this particular approach, we needed to indoor and, let's say, safe environments. Thank you.